Hey, it's Warner, and let's take a look at some Gaussian problems. So we've got a couple of different shells here. They are both non-conducting, so we want to make sure we underline the things that are super important. Non-conducting, they are spherical. So make sure you see that they are not just flat here. It's actually a shell, so it'd be kind of like a ball that's hollow in the middle. They tell you what the surface charge density is. And if you remember, there's different types of charge density. There's linear charge density, there's surface charge density, and then there is volume charge density. And so we're used to volume charge density because this one is something per unit volume. So for the linear charge density, all we would do here is it's the charge per unit length. This one is the charge per unit area, and this one would be the charge per unit volume. So we're really going to take a look at this in order to help us. Our information that we've been given is we know that right here at the middle, this is our 0 position. We know that the radius of this one is 3 centimeters, so 2 centimeters is going to be where that red dot is, and we know the surface charge density. For shell 2, we know that the center right here is at 10 centimeters, or 0.1 meters, and we also know the radius of that second sphere and the surface charge density. So to find the electric field from shell 1, what we need to do is determine that point P relative to the shell. So we notice it's inside the shell, and because it's inside the shell, Gauss's law basically just says that the electric field inside a uniformly charged spherical shell is just 0. So that one, pretty easy to do. For the second one, define the electric field from shell number 2. So remember, we've got shell 2 over on the side here. We have shell 1, and then we have our point of interest right here. So we need to find the distance from point P to the center of shell 2. So we want to go from here all the way over, and we find out that that is about 0.08 meters. And the way we did that is we just said we know that we want to go from that 2 centimeter to the 10 centimeter, and so when we go through and solve for that, we end up with that 8 centimeters. This is somewhere outside of shell 2, so now we can actually go through and solve it. So first thing we're going to do is we're going to calculate that total charge Q2 on shell 2. So that's just the surface area density times the area. We know the area is 4 pi r squared, because you'd have to look that up for that shell. And then we can plug all our values in, and we end up with a charge of about 2.01 times 10 to the negative 8. So that's our Q2. To calculate the electric field, we're going to use our electric field equation, which is just KQ over r squared. We know K, we know what our Q is because we found it here, and we know that the radius or the distance between those 2 points is 0.08 meters. So when you do your math, you end up with 28,244 newtons per coulomb. Let's go ahead and take a look at the next one. This is a uniformly charged conducting sphere of 1.2 meters, so we see that's its diameter. Has a surface charge density of about 8.1 microcoulombs per meter squared. So they want us to find the net charge on the sphere and the total electric flux leaving the sphere. So to find that net charge, we're going to have to multiply our charge density and the surface area of the sphere. So remember, if we have surface density, that's equal to the charge divided by the area. So if I want to find the charge, and you can either use capital Q or lower q, that's just going to be equal to the density times the area. So the diameter is 1.2 meters, so our radius is 0.6. we have to use the surface area of a sphere equation, which is 4 pi r squared, plug everything into that equation, and we get our answer for the surface area. We also now need to find that net charge, so we're going to plug in that 8.1 microcoulombs per meter squared times what we just got for surface area, and that tells us what that net charge is. Now that we have net charge, we can use Gauss's law to find out what the flux is. So remember, flux is just basically the amount of charge that's going through a certain area. So it is probably better known as Q enclosed, so that's the amount of charge that is inside, and we just found that up here. And we're going to take that and divide it by the constant for the permittivity of free space, which remember is 8.85 times 10 negative 12th. So when I do that math, I do end up with flux of 4.14 times 10 to the 6th newtons times a meter squared per coulomb. For the next question, this one's a little longer. So this one, they have a charged particle. It is at the very center. So right at the center, that black dot is that charged particle. And then there's two concentric conducting spherical shells. So you have to think about this as like a golf ball inside of a tennis ball with a charge inside of that golf ball. And they give us the flux in terms of radius, and you see that the flux starts down here, and then it shifts very quickly to 0, and then it shifts very quickly to a positive value, and then kind of makes its way back as you go through the radii. So for any radius r before shell A, that Gaussian surface only encloses a central particle. So what they're saying is this Gaussian, that for, for any radius before shell A, so that's any radius here, we only have just this, if that's our Gaussian surface, because remember this is real, that's real, so the blue here is just a fake thing that we call the Gaussian surface. So if we want to know what this is, we know that it's -2 times the flux of that surface. And so they told us that we have 5.5 times 10 to the 5th newtons times a meter squared over a coulomb. So that's our flux. And we know for the particle, it's -2 times that. So we end up with a flux value now for the particle of -1 times 10 to the 6th. To calculate the actual charge of the particle, we know that the enclosed charge is equal to the flux of the particle times epsilon naught. And so because we already know the flux of the particle, we can take that, multiply it times epsilon naught, and that gives us the charge of that central particle. For part B, they want us to find the net charge of shell A. So remember, shell A is the one here. And to do that, we're going to basically just say that for any radius between shell A and shell B, the Gaussian surface encloses the central particle and shell A. So now we're going to draw another Gaussian surface. It would just be another sphere. I can't draw a circle for some reason tonight. But notice that that imaginary dotted surface has inside of it that particle, and it has shell A. So to find the flux value, to go through, we need to find the flux value. So we know that for shell A, that is equal to the positive flux, so we end up with 5 times 10 to the 5th newtons times a meter per coulomb. And where did we get that the flux in the region is this value? Well, if we look at the table here and look at the graph, we see that the flux in that region is basically just positive the phi s. And so that's what we see. So that's, and remember, because the scale of the vertical axis is this guy right here. So if we come back down, we find out that since we know the flux value, we can calculate the total enclosed charge. And so we're going to just take the flux times epsilon naught again. We got 4.425 times 10 negative 6. Now we want to find the net charge of the shell. So that's QA. So remember, we have the particle inside, and we have our shell, letter A, and we drew a Gaussian surface around both the shell and that central particle. So if I know the particle charge and I know the outside charge, the enclosed charge, then I can subtract the two, and that gives me the net charge of just this shell that's filled in. So notice we just took our enclosed is both the particle and the shell A, and rearranged it for shell A, put our values in, and we end up with this answer. Finally, for any radius outside of shell B, the Gaussian surface that we're going to draw here, so here's our Gaussian surface, it now encloses everything. And because it encloses everything, we can find the flux value by saying, well, it's equal to negative phi s. And so negative phi s would be right here. We're going to take the Q enclosed times the flux of B times the epsilon naught. We know flux of B, we said, is just equal to this guy. So it's now negative 5 times 10 to the 5th times epsilon naught again. And that gives us negative 4.425 times 10 to the negative 6. So that's the total charge from A, B, and the particle. And we just want the charge from B. So we rearrange the equation, plug all our numbers in, and then we end up with the charge on surface B. Let's go ahead and take a look at this next one. And this one is the uniform linear density of 2 nanocoulombs per meter is distributed along a long, thin, non-conducting rod. So the rod is this thing on the inside, and it has all of the charge on it. And notice it's linear density, and linear density, remember, is equal to the charge divided by the length. So then they tell us the rod is coaxial, which means that its axis, or that arrow pointing towards it, is the same as the axis for the shell here. So, and it gives you an inner and an outer radius. It says the net charge on the shell is 0. So they want to know what's the magnitude of the electric field 15 centimeters from the axis of the shell, and then they want us to find what's the surface charge density of the inner and the outer shell. So the inner shell would just be this piece right here all the way around, and the outer shell is going to be the outside of this tube that we've got. So to find that electric field outside the entire assembly, because we know that the inner radius is 5, this is 10, we're going to use a Gaussian cylinder. It's the dotted line that you see here. So the Gaussian surface does enclose everything. We're going to start with the linear charge density of the rod, which is 2 nanocoulombs per meter. And that is basically just 2 times 10 to the negative 9th. So the net charge on the shell itself is 0. So the linear charge density of that shell has to also be 0. So now we know that the enclosed linear charge density is equal to that of the rod plus the shell. Well, the rod we said was this, and the shell is this, so now we know what it is. So now we've got that enclosed charge. We're going to apply Gauss's law now for the cylinder. And you can do it two ways. You can either say that E is equal to lambda enclosed over 2 pi epsilon naught times the radius, or you can use the fact that K is equal to 1 over 4 pi r epsilon naught. And you can say 2 times ke times lambda over r. So either way you do it, it's fine. I think the book tends to do it with this first equation. So we're going to go ahead and do 2 times 10 to the negative 9th. Remember, that's what we found up here. That's our lambda. And then we have 2 pi times epsilon naught times that radius. And remember, we said that it's 15 centimeters or 0.15 meters. So we get 239.8 newtons per coulomb. And that would be the electric field value. Next thing they want us to do is find the surface charge density on the inner surface of that, that cable, that coaxial cable. So it's this big blue part here, and we just want the inside of it. So for the inside of the conductor, we're going to think about a Gaussian surface with a radius between the inner and outer shell. So if I get rid of what I have here, our new Gaussian surface, and I'm going to make this one purple, is going to be right here. So it's in between the two. So remember, it's an imaginary surface so we can see what's enclosed. So the two things that are enclosed here are the rod itself and the inner part of the shell. The outer part of the shell we're not going to worry about. So here we've got the rod plus the inner part of the shell. Linear density is equal to 0. And so therefore we could say that the inside of that shell is equal to the opposite linear density of the rod, and that would be negative 2 times 10 to the 9th. To find the surface charge density now, it's really, remember, surface charge density is just equal to the charge divided by the area. And so our the inner radius is 5 centimeters or 0.05 meters. So the inner surface charge density is the linear density divided by 2 pi r of the inside. So there's our value that we have here. And then 2 times pi times that 0.05 for the inner radius. And we get about 6.4, negative 6.4 nanocoulombs per square meter. For letter C, this one, they want the net charge on the shell is 0. So that means that the sum of all those charges on the inner and outer surfaces is 0. So we know for the shell, the inside plus the outside is equal to 0. That means that the outside is equal to the opposite of the inside, and we know that the inside was negative 2 times 10 to the negative 9th. So if you make that negative, 2 negatives make a positive. So now we have the linear charge density on the outside. So now we're going to say that radius is 0.1. We're going to do the same thing we did before, but now we're going to use the positive value since it's the outside linear linear density over 2 pi r out, and we get this value. So one thing that's confusing about this is we keep going back and forth between linear charge density, which is equal to the charge divided by the length, and area, which is the charge divided by the area. So what you can do is you can say that this is actually equal to the linear charge density divided by the area. And so if you do that, kind of like what they've done here, so we know that this out is equal to lambda out over the area on the outside. So that's why we're able to do that.